Good morning, class, and welcome to this lesson on Kinematics 13 projectile example number 1. Today we will be able to solve for the following projectile motion problem. So these next few videos are just going to be example problems, just to try to solidify what we're trying to learn, okay? So let's say someone is standing next to a building, okay? And they are throwing an object at the building, okay? This person knows that the max velocity they can throw is 15 meters per second, and they know the best angle they can throw this at is at 60 degrees. Okay, so this person is throwing an object up to the top of a building, is trying to get as high as possible, as high as possible. So the question is now, how far do I stand away? How far away do I stand? Okay, so kind of a random situation, but a good example problem. So we're going to use our two problem-solving strategies in order to solve this. So let's start. First thing, this person is throwing at an angle. So we need to break this down into its x and y components. So let's do the y component first. The y component is going to just be the vertical component of this vector right here. And so that's going to be, this is going to be the sine of 60 times 15 meters per second. How did I get that? When I look at this triangle, 15 is the hypotenuse, this is the opposite side, and the sine of 60 is going to equal the opposite. I'll call this y. Okay, y over 15. So y is equal to 15 meters per second times sine 60. So that's how I got this number right here, okay? So the sine of 60 times 15 is going to equal 12.9 meters per second. Okay, so because this is going as high as possible, what we're saying here, this is at the top of the arch. Okay, so this thing is being thrown, it's making a nice smooth arch. This highest possible point is going to be the very top of the throw. Okay, so what does that tell us? That tells us at the very, very top of the throw, the velocity in the y direction is going to be equal to 0 meters per second. Why? Because y and x velocity are completely independent of one another. So even though this thing is still moving this way, it still has an x component of the velocity, the y component is 0 at the top of the arch, okay? It's still moving. It still has an x component, but the y component, as we move up, is going to get less and less and less until at the very top the y component is equal to 0. So the first thing we are doing is we are breaking this up into its x and y components, which is the key part of these problems. Next, we're going to solve for time. How long was this thing in the air? Time is the factor that will tie together x and y, okay? How long it spends in the air in the y direction is how long it's going to spend in the air in the x direction, okay? Time is not a vector. Time does not matter. So I have my initial velocity in y is 12.9. My final velocity in y is 0. My acceleration is negative 9.8 meters per second squared. I'm making this negative 9.8 because I'm saying that this is 12.9 meters per second in the positive direction. So acceleration due to gravity is going to be pulling it down. So this is negative 9.8 meters per second squared. So I have initial velocity, final velocity, acceleration, trying to solve for time. I am going to use this equation right here. I'm going to put Vy final equals Vy initial plus AT. Okay, Y final is 0 meters per second. This equals 12.9 meters per second plus negative 9.8 meters per second squared times t. Okay, so we have negative 12.9 meters per second equals negative 9.8 meters per second squared t. Divide both sides by 9 or negative 9.8. And what we find is that our t is equal to 1.32 seconds. So this thing is going to take 1.32 seconds to get to the very top of the arch, okay? If we throw it at a 60-degree angle at 15 meters per second, okay? So that's the y direction. I will draw the picture again over here. Person is throwing. Initial speed is 15 meters per second. This is an angle of 60. In the y direction, we had 12.9. And we know this is going to be in the air for 1.32 seconds. Okay? So now we have to look at the x direction. Okay? Because at the end of all this, we want to know what the distance is, right? That's our final thing. So what we know about the x direction is that velocity is constant. Velocity is constant. Okay? So so in the x direction, I should put that in the x direction, velocity is constant. So when we have constant velocity, we can use this equation right here, v equals delta x over delta t. We are trying to solve for this. Okay, we're trying to solve for the displacement in the x direction. We know that time is equal to 1.32 seconds. And so the question is, what is the velocity in the x direction? Okay, because we can't use this. This is the velocity total. We can't use this. This is 12.9 meters per second in the y direction. So let's find out what the velocity is in the x direction. So what is the velocity in the x direction? Well, we have a triangle here. So the cosine of 60 is equal to the adjacent. I'm going to call it Vx. Okay, this is Vx over 15 meters per second. So Vx equals 15 meters per second times cosine 60. So this is going to be equal to 7.5 meters per second. So 7.5 meters per second equals delta x over 1.32 seconds. Delta x equals 7.5 meters per second times 1.32 seconds, and we get an answer of 9.9 meters. Final answer. So let's go back. Problem solving strategies. We can never use the velocity given when we're trying to break it down into components. Okay? We cannot use this number for the velocity in y. We cannot use this number for the velocity in x. Okay? So we have to break this down. We have the velocity in y right here. So using the velocity in y, we were able to solve for time. Time ties together x and y. So we moved over. We found the velocity in the x. The velocity in the x is constant. So by knowing the velocity in x, all we have is a simple distance problem saying if we have this velocity and this time, how far away is it? 9.9 meters. Okay, so we use all of our problem solving strategies, breaking it down into components and using time to tie it together to solve this problem.